So in this video, we're going to look at two problems from Pinter, which I know is a little bit counter to our usual methodology here, but the two problems are two sides of the same coin with regards to equivalence relations and partitions. So it seems like it's a good idea to kind of show both sides of the story at once. So the first problem we're going to look at is 12.A.1, which goes as follows. For each integer r in the set, that is a really cooked brace, but it's fine. 1, 2, 3, 4. We have the set AR, which will denote the set of integers which leave a remainder of R upon division by 5. And the question is to show that these actually are a partition. And so what do we have to do for that? We have to see that the AR are non-empty. The AR are disjoint. That their union is the whole set, which is obviously Z. We're talking about integers. And let's see, how do we dispatch with these? I think each of these things might be kind of easy to observe individually, so let's kind of put them all together. Non-empty, of course, each of the AR are non-empty. Each of the ARs contains R, right? All of these are candidate remainders upon division by 5. So if they're also all numbers less than 5 because they're remainders. And so if you try to divide any of these by 5, you get itself. And so R is in AR. Are the AR disjoint? What this means is, can I have an integer in AI intersect AJ for I different from J? Well, what this would mean is this guy means that if I divide Z by 5, you get a remainder of I. Whereas this guy means that if I divide Z by 5, I get a remainder of J. But when I actually do the division, every number has one concrete remainder. Right? You can't have two different remainders because it's just a matter of doing the arithmetic. And so the answer is no, this can never happen. And so these are disjoint. Lastly, is the union of all the ARs equal to Z? In other words, does every integer belong into one of these classes? The answer is yes, because the deal with the division algorithm is when you do any kind of division, you get some number as the, let's write it this way. You have a quotient times 5 plus a remainder. And the deal is that 0 is less or equal to R is less than 5. And that's exactly the 5 things that we've got here. And so every integer has one of those 5 outputs. So we're done. So this is a partition. Let's look at question B4 now, which is very similar. And also, I'm going to tweak the question a little bit so you guys can sort of see how it works. Make them kind of more compatible, the other side of the coin. In the part B, we have to prove that each of the equivalence relations that's given actually is an equivalence relation. And the equivalence relation here is an equivalence relation on Z. And in the text, it says that integers A and B are equivalent exactly when A minus B is a multiple of 10 in the question. We're going to use 5. So that way it fits with what we've been discussing before. I know it's a little bit of a change. In any case, I have to prove this is an equivalence relation. So let's see. For symmetric, 5 times n for some n, right? A multiple of 5. So this n is an integer. Otherwise, what I was going to say is not going to work at all. Symmetric. A is equivalent to A. Well, that means A minus A is a multiple of 5, Well, a minus a is 0, also known as 5 times 0, and so a is equivalent to a. That is not symmetric anyway. That is reflexive. What's wrong with me today? Sorry about that, friends. For symmetric, that one says if a is equivalent to b, then b is equivalent to a. Well, if a minus b is equal to a multiple of 5, then b minus a is equal to minus a minus b, which is minus 5, right, by applying the previous equation. And so that is 5 times minus n. So still works. Opposite multiple, still a multiple of 5 nonetheless. Lastly is transitive. When I was in school, I had a professor. I'm not saying this is a nice thing to say, but it's a funny thing to say. Hopefully, you guys will agree. He used to say, whenever we have an equivalence relation, I won't insult your intelligence by checking anything other than the transitive property, because as you guys are getting here, usually these two are very straightforward. This one requires a pinch of thinking. So if A is equivalent to B and B is equivalent to C, is A equivalent to C directly? So this one tells me that A minus B is equal to 5n, some integer n. This one tells me that B minus C is equal to 5m for some possibly different integer m. And the question is A equivalent to C directly? So what we're going to do is actually add these equations together. And now, through the power of algebra, obtain 5n plus m. All right, so this is where the problem part would stop. But what I want to do is just take one more moment and emphasize to us that this is exactly the explanation that we were talking about in the chapter main video lesson, right? That these are the same information. In other words, this partition gives me this equivalence relation. Why? Because if I have two elements that are in the same R, let's write this down. Let's check these are the same. If A and B are both in AR, then what that means is A equals some quotient times 5 plus that remainder, and B is equal to that some different quotient, maybe I'll call it Q prime, times 5, also plus R, right? They have the same remainder when you do division by 5. On the other hand, A minus B is 5Q plus R minus 5Q prime plus R, which is 5Q minus Q prime, and the R's exactly cancel. So being in the same AR means that your difference is a multiple of 5. Similarly, if your difference is a multiple of 5, then we can conclude that the R's are the same. For example, let's say this is 5Q plus some R1. This one is 5Q prime plus some R2. We don't know that their remainders are the same. If it turns out that their difference is a multiple of 5, then when I subtract them, sorry, this should be a minus sign. If I group these things together, I get 5Q minus Q prime, just like before. And then we get R1 minus R2. These are both divisible by 5. The only way these can be, the whole thing can be divisible by 5, because these range from 0 to 4. R1 minus R2 ranges from -4 to 4, depending on the order, like, which ones go where. But the only way that that can be divisible by 5 is if they're actually 0. So this is illustrating the point that I was making, that equivalence relations and partitions of sets carried the same information with this very basic but extremely important example, because, in case you didn't, notice by now, these remainders are the equivalence classes that we use in Z mod NZ. So this is a classic group theory example, just explained in terms of basically set theory.